Okay, sorry about the delay. Thank you everybody for coming here today this morning to my thesis dissertation. My dissertation is on understanding images and videos using context. So we will be talking a lot about context. What we understand by context is any information that may influence the way that understand images and videos. So this is an image without any context. If I show you the global context, your perception completely change. So this talk, it will be about three chapters. Has three chapters. One is understanding image content using context. The second chapter will be finding the shared context from multiple images. And the third one will be improving understanding on videos using context. For image understanding using context, so this is how object detection looks like. You have bounding boxes and you know what's the class and what's the possible score. So unfortunately, this picture is somehow incomplete. So in this case, the context is not considered. If you have a lot of categories, you start having ambiguity, and there's no way to know the relationship between different bounding boxes. They are like independent one from each other. Also, there's a bunch of bounding boxes there, but there's no way to know which one is more important than other. So so we will deal with that problem. The next problem we're going to deal is finding the shared context for multiple images. So the idea in this problem is you have a person here, let's say, using a wearable device like that one, and that person is capturing some images like the ones you are seeing there, right? So the idea is to come out with a system that automatically is able to come out with the common context that all these images share, which in this case will be something like buying a jewelry in a store or something like that. Finally, the third problem deals with videos. So the idea is like we're going to do a scene identification. So the videos looks like this and are performing daily activities. And the idea is to come out with a label for each one of the scenes. In this case, will be a kitchen for each one of the frames. Sorry. And also, we are going to try to improve object detection. So in this case, we have an image like that corresponds to a kitchen. So there are certain objects that are more common in a kitchen. So we are going to using that to improve object detection. Okay. So we're going to jump into the first topic, which is understanding image content using context. So this is an image, and this is the object detection results. So this is nice and everything, but as you can see, you have here a stove. And the reason for that is because we have had a lot of classifiers, different classes. So as long as you start in more classifiers, you start having this kind of ambiguity. We also have here a pillow detector, but unfortunately, we don't get any detection here. Interestingly, we have a bed detector, and it gets detected a bed. But because we don't have any relationship between bed and the pillow, the system is not able to detect it. So we try to elaborate those relations. Finally, there's no way to know like what object is primary or secondary there. And in general, what is missing here is an holistic view about what's going on in that image. So if I ask you guys, like, what do you see in this image? You probably will tell me something like, okay, there is a bed here, there is a window here, there's a wall there, and there is a desk here. And actually, if you go further, you might tell me, okay, this window has drapes, and this bed has a doll and a pillow, and this desk has this lamp and a clock, and this wall has this piece of art. So as you can see, like the image has some structure, and what we want to do is model that. And a nice way to model that is through a tree like this one here. So our problem, we are going to define it clearly. Is even at this image, what we want to do is identifying region or bounding boxes for the objects, exactly as you do in object detection. But in addition, we will want to identify the hierarchical structure that they have, as I showed, like parts, subparts, and so on. And also identify what are the most salient objects on that image. So in order to do that, we have defined this image representation. It's a tree, top-down visual tree. And the idea is like you have an image like this. You start from a root node. This root node represents the full image. And this node has associated several objects. So in this case, these are the main objects on the image. For example, this one is the man. That man here is the most important object that you can obtain here. And then there are other secondary main objects like this other man, this building, the sidewalk, and a street. So the order of these branches indicate what object is more important. And as you can see, each one of these parts or elements can have subparts. So we have depicted in green what we call left dependencies that corresponds to parts or attributes. So in this case, that man has sneakers, shirt, glass, and so on. And we have another type of dependencies, which is right dependencies, which model parts that are not necessarily part or attributes. Like, let's say that arm is not necessarily a part of a jacket. Okay, so the problem is really clear. You get this input here, and we want to output like this. This is actually a real output. So as you can see here, you have the image, and you are able to identify what are the parts on that image. And so let's say the most important object here in that image is the street. And this street has a sidewalk, a car, a people, tree. And other secondary objects are this building, which has a window, and so on. You see all the structure of that image. Okay, so that's what our output. So now, how do we do to learn that? In order to learn something, we first need like data from where to learn. Obviously, we cannot find this TDVT there. So what we do is like we are going to parse a data set that comes from object detection to obtain many of these trees, and from them we will be doing learning. So the idea is we get images with annotation from object detection dataset and do a parsing process and come out with those trees that we will be using to learn. So then we pass this to a training system and we will be learning. Okay, so how to do this dataset parsing? This is a pre-processing. It's through these 5 steps. So the first step is you get from the annotation from object detection datasets, you get many bounding boxes that are have high overlap, and they are really close semantically. So what we do is to prune those to remove duplicate objects. So we use distance in the WordNet ontology. Then we look for relations between parts. So in this case, man and shirt are related. They are close semantically, and the bounding box is inside one of the other. So in this case, we can relate them. So we relate them for every part of objects. And at the end, we will have something like this. So this is a graph, but it's not a tree. And what we are looking for is for a tree. So in order to, the problem with that is like we see a lot of loops here. So in order to remove loops, we use a minimum spanning tree algorithm, and we are able to come with something like this. And after that, then we have like a main trees, but we have like a bunch of isolated nodes. So in order we remove those isolated nodes, and at the end we come up with a nice tree. The problem with the tree is like the branches there are not sorted by order of importance. So you use the saliency measurement to sort them. In this case, we have a saliency map, and we have bounding boxes for each one of these objects. We compute the density and sort them based on that. So this is our examples of the output of after we do the dataset parsing. So you see the image here, and these are the main objects. You see the person, the car, the building, and this is in general the tree we got. So so this is what we will be using to train our system. And this is another example. So the main object there is that screen and that glass of wine, the keyboard, and this is the tree we obtain. And of course, you get the subparts, like this screen has these pictures and so on. So we will use this to train. Now, instead of explaining the training steps, I'm gonna just show you the inference step, because you will see how this works, and then later we can see how the training process is done. Okay, so essentially we will have these three parts here. As you can see here, there is a gray, and this part in gray will take care of all the scores. So this is a well-known algorithm which is called FastRCNN. And then we have this part here which is in orange and takes care about the branches. And we have this part here which is in blue and will take care about the labels. So I'm going to show only these two parts meanwhile. And essentially what you have here is an input, and we will display in this area here what will be the output. So we are going to start building that output just to show you how to do that. So we obtain visual features using the convolutional neural network, and we start building the tree here. So we start always from the top node, which represents the full image, right? And so with that, because we know it's the full image, we do pooling, get a visual feature, and we pass it through this building block, which determines if there is a branch or not. So in this case, we have 4 classifiers. The first classifier is telling us if there is a left branch or no. If there is a left branch, like as in this case, then we start building the output. Okay, there is a left branch. So now we know there is a left branch here. So what we want to do is pass that to this bounding box here that takes care about finding the label. So the idea is, what could be the label associated to this main figure? So in this case, it predicts that there might be a bed or a boot, or actually there's a list of stuff that it can predict. So what we do now is like check in this scoring part, we check the object proposals and see in a reduced set of classes what will be the one with highest score. So let's say this one is the object proposal with highest score, and we know it's a bed. So then we have our first sibling here. Okay, so we just continue this process over and over. So let's say we go to this node and we check if there is a right branch. If there is a right branch, then we put it as an output. Then we try to look what are the possible labels that appear there. So we feed the system here, and we try to predict, and there's going to be a window maybe, and a wood maybe. So we just check the object proposals and just keep doing that. And so we check the object proposals, we pick the one with highest score, and that's it. We get the second node. So we just keep doing that, and that's the way to build the tree. As you can see, there are four building blocks here. So the reason is like there's one building block for the relations that are next to the left, and there are another to the ones that are next to the right. So we have 4 classifiers that determine for different different dependencies. Okay, so I explained already how to do the inference process. So now I'm going to explain how to do the training process. So the training process is simple. The gray part, you already know how to do it. It's FastRCNN. I'm not going to explain that because it's really well explained on literature. But then we have this part that takes care about labels, so I'm going to explain that. And then we have this part here which takes care about the branches. So that's so I'm going to explain briefly that. So the idea is like you have this input image and you have this from your training dataset, so you know this from the ground truth. And the idea is like you start doing pooling from top, get the visual feature, and you pass it to this block. So the inputs to this block are the visual feature and the fact that you know there is an initial left branch. So this initial left branch is used to select here one of these 4 units you see here. And the idea is from that get an output. The output in this case will be man. So we want to predict there's going to be a man there. So we encode this as a one-hot vector. And we're going into the detail what this unit has inside. So inside these have 4 LSTM units. So each one of these LSTM units take care about one of the 4 type of dependencies I explained a moment ago. And these are regular LSTM units. The only difference with regular LSTM is like you have here the hidden vector outside, and it's shared by all of them. So in that case, this H is the one that takes care about context because it's seeing all the image all the time. So that's pretty much how the training works. So you have the input, which are the visual feature and what type of branch you are going to select, and the output, which will be what is the possible label is going to be linked. And you just start doing that for every pair of nodes that you have there. Okay, so that's the training process for labels. For branch, it's just simply 4 classifiers. So we have 4 classifiers, one for each type of branch, and the data we need to do that, it comes again from these 3. So we know the visual feature and HT that comes from the previous slide. And the idea is for this node, does it have an initial left dependency? In this case, it's clear that yes. So we use this as a possible training data. So we have yes for these 2 inputs and this output, and just keep doing that for every possible classifier and for every possible node. So we just do that, and we have the data to train the classifier. The classifier could be anything. In our case, it's a multi-ledger perceptron. So that finished the theory. So we're going to the experiments. We did experiments with visual genome dataset. So this is a dataset with 108,000 images. And we picked the 2,000 most common categories from these training data. The details about the network is we use BGG16 network. The object proposal method is HBox. And these are the details about the top-down 3 LSTM and the 4 classifiers. So here I'm showing you the results, which goes beyond what you can obtain with object detection. So you have an image here, and in this case we have like the main object here is a street and row, and this street row has 3 person, other person's pole. So this is really cool because you cannot do that with traditional object detection. This gives you something else that object detection don't give you. And you know, like there are other additional objects like these cards. They are from less importance in this image. So we have multiple examples like that. So in this case, the most important object is the sky, and the sky has these lights, 3 poles, signs, and building. And there are other important objects like the street road and the cars. These are also another example. This is an example that I already showed a moment ago. So you have the street and the sidewalk and people window. And this is another nice example. You have the train. This is the main object. This is clearly the main object here. And you can see like the train has windows and doors. And there's a secondary building and the sky. And the skies have these lights and traffic lights. So this works pretty well. And it's really a nice output like we are producing here. So in order to evaluate that, what we did is a user study. So we asked to Amazon Turkers, 119 of them, and we asked them like if those trees represent properly that image. And each image was evaluated by at least 7 different Turkers. And when we did that for the images that we parse directly with the algorithm, 86% of people say that they were a good representation. And when we tried with the testing images like our system didn't know with anticipation, so 85% did it. So that's good. So people somehow agree like these trees represent properly the content of the image. And we also look at like, because we are able to find what are the main objects, we want to compare like what are the main objects between our system and what are the highest score for FastRCNN, which is an object detection method. So as you can see here, we are able to identify as the main objects these boats and these buildings, which were not previously identified. In this image here, for example, we are able to say like this building is an important object. So of course it's more important than a window. In this case, for example, we are able to find like the monitor is an important object in this image. Or in this case, for example, this is signaling this window as something important, but we get this woman, which is a lot more important, and so on. So another way to measure like the effectivity of that is through object detection. So we compare the results of the 2,000 categories I mentioned. So of course there are many I cannot put this on the screen, so I just put 44 of them here. And so these are the different results. So the FRCNN is FastRCNN, and the other is ours. As you can see, we outperform the other method in many categories. And actually, when we check the mean in the 2000 categories, we almost double their MIP. So also a nice thing about that, a nice experiment we try with this is like we try to see how these models that we learn on visual genome dataset behave in a different dataset. So we tried this in some 2012 dataset, and in that case, only 950 categories out of the 2000 mapped correctly. And what we notice is that we get an improvement, relative improvement of 21%. So this is also quite remarkable because this seems to work across datasets. It's not like we are overfitting the dataset somehow. So in summary, this part of the talk, we present a new TDVT image representation. So we present a method to extract this TDVT representation from the image detection dataset, algorithms for learning and inference. We improve object detection for a large number of categories, and the gains in object detection are kept across datasets. Okay, so that finished our first part, which is how to use the context to improve image understanding. Now we will see a second part, which is how to find the shared context from multiple images. Okay. So given a set of images describing a topic like this one here, what we want to do is being able to describe what's the context that relate all of them. So in this case, the context will be an output of 10 words, like this one here. So the possible applications for that are visual context discovery, and I think we can enable semantic search with that, and video summarization. The proposed framework is like this. It's based on image retrieval. So we have images, we have a descriptor, and we retrieve images. And from that, we want a list of words that, as you can see, every retrieved image has associated some words. So we pick from that some words, and we do that for every query that is there. So from that, those lists of words we have here, we come up with a single list of words, and finally, after we apply context, we are able to come out with the final answer. So the image retrieval is very simple. You just get the image, get the descriptor, and match with images, and just pick the closest Euclidean distance, and you obtain images like this. Then these are examples of these retrieved images, and then what we want to do is obtain a list of words. So in order to do that, this is the query image, and this is an example of retrieved images. So each one of these contains some text associated. So what we want to do is like images that really look similar to the query image, we want to give it more weights to those words. So in this case, we check the distance in the visual domain between them, and we weight all these words based on that. So we just keep doing that for every retrieved image. Like in this case, this will be have a different weight based on the similarity between these two images. And at the end, we sum all these weights and be able to come out with a histogram like this. So this is for the input image 1, and this will be for the input image 5. So from that, we want to come out with a single joint representation that relates the different queries that we have here. So each one of those represents the histogram for each one of the query inputs. So what we do is really simple. We just threshold this, and we ignore all the words that are considered as noise. And for the ones that are over that threshold, let's say hurricane here, so we count this, we make an histogram from that. So then this will count 1. There's another hurricane here, so it will count as 2. So our final representation will be something like this. You get hurricane here, and it has 2 counts. So we just do an histogram of the surviving words. And after that, finally, we apply context. So in order to apply context, we simply check that they are very related words. Like you see, these words are very related, and they are very unrelated. So we want to give a higher rank to the very related words because that are the context. So in order to do that, we do a random walk. So in each node, every candidate word will be a node, and the edges between them are given by the word-to-back distance. And we apply the random walk, and we update that. This random walk algorithm is the same that it's almost the same that Google used for page ranking. So things that are similar, like in this case, like this case, storm, weather, and snow will be highlighted, and words that are unrelated will be out. So our output in this case, we will see like the words that we are not able to match correctly still are semantically very related. So the experiments for that, we use as a retrieve dataset, Bing dataset. We use visual features from CNN, and we use LSH methods for approximation. This is the dataset we use to do the experiments. This is a public dataset that contains 300 topics, and each of them has 20 images, and it has the top 10 most representative words for each topic. So these are the images for one of the topics, and this is the ground truth that we have here, and we are able to we are able to find correctly 6 of those words. So this is quite difficult because it's an open dictionary. There's no like we have a list of 20 or 300 words is open, so it could be any word. So it's actually really hard to actually get the real words. This is another example. We get 5 correctly. In this case, we get 4 correctly. And so in order to do this quantitatively, we use the Jacquard index to measure the performance. So the blue line is our baseline, which is before doing the random walk. And as you can see, when after we apply context, we get a lot of improvement. Obviously, when you start adding more images, you obtain a better performance, and that's because, like, if you have more images, you have a clear understanding of what's the context of that. So with that, we apply this to another problem, which is image retrieval. So in image retrieval, traditional image retrieval looks like this. You get an image, and you look for images that looks similar to the query image. That's what you do with Google Images or whatever. So what we're proposing here is like, but instead of doing that, we use multiple images as query images. So in our case, what we are looking to do is like find out what is the shared common context between these 3 images. So in this case, for example, what we do is like we will try to receive cattle or cow, which is the concept that somehow relate the 3 images, because cattle and cow produce milk and meat, and cattle and cow are kept on farms. So we pass these 3 images as a query, and what we get is images like this. Again, our approach is based on in the present framework. We get retrieval images, we get a joint textual representation, and the only difference is like we do term frequency, inverse document frequency to retrieve the images. So we did experiments with pairs of input images. For example, here we have a dog and a house. So somehow the concept that relate these two are kennels, and then the retrieved images looks like this. So we have also, let's say, this car and this house. So somehow the concept that relates them is garage. So the image that we retrieve look like this, like a lot of garages. So yeah, so this is a new paradigm somehow, and so we have here a car and a bed. So we get to retrieve our strollers, and here we have a car and a bike, and the type of images that we get back there are motorcycles. So to evaluate this, we did it also through a user study. So what we did is like we presented 101 pairs of images like the one I just showed you, and asked them to say if they are a good representation of the query images. And so we see when the baseline is just aggregating the output of the different query images, And as you can see, like around 55% people say, okay, it's fine. When we did in top 5, then in top 10, top 15 images that we retrieve. But when we show our results, we get a lot of improvement. Also, people feel like this is a better representation of the query images. So this is actually really nice, and you can go right now and try this. There's a demo available online, and try it. So this finished the second part of the talk. We come up with this new problem of finding the shared context of group of images. We also have a new retrieval application where the retrieved images are conceptually and visually meaningful. And so now I'm going to move to the third part of the talk, which is how to do improving understanding on videos using context. So we will be dealing with videos like this. Those are videos of activities of daily living. In this case, this guy is probably cooking or something like that. And so the idea here is that we are going to solve two problems. One is improving identification using the temporal context. Another problem we're going to solve here is improving object detection using semantic context. So for the scene identification, we assume like we are in a known scene identities like kitchen, bathroom, laundry, and so on. And the reason to do that is because humans perform these activities in known places. So we have NS number of scene identities, and we train a classifier for each one of a scene. So we train a classifier for kitchen, one for bathroom, and so on. And we periodically sample that. And so the goal is to find the right labels for each one of these scenes. So N is the number of frame sequences. So this is the video that we are dealing with. So these are the sample frames we are getting, and these are the different scores we get for the different classifiers. So as we can see, these two are correct, but in this case we have failed identification. So in general, we get these two which are failed. So the idea is how to come up with a method that fixes that and says this is a kitchen. So in order to do that, we have this CRF formulation. So in this case here, each one of these blocks here is a frame. So we have the first frame, the second frame, the third frame, until the frame number n. And the idea is come out with a good set of scores, good set of labels for y. Each one has an observation. So in this case, we have 3 different observations, which are the scene classifiers. So in this case, will be one for, let's say, kitchen, other for bathroom, other for, I don't know, garage. And we have links that connect temporally these nodes. So this will be the equation that describes this CRF. And we have this term, which is a unary term that takes care about privileged labels with high scores. And we have this pairwise term that takes care about this temporal constraint. So so at the end, we will be minimizing this energy function. So this term is the unary term. So you get a low value for high scores. And this is a penalty, like if you have change on the scene identity, you will have some penalization. So this metric has zeros in the diagonal and positive values that tells how much penalty to add. So that finished the improved scene identification. So now we'll see how do improving object detection. So in this case, the constraint that we're going to use is you have an image like this. In an image like that, you know there are certain objects that cannot be there, like a telephone probably will not appear in a kitchen, but a coffee maker most likely will do. So the key image here is this. So we have here results only for microwave, for the object microwave. Each dot of this is a detection result. So here in the XYs, we have the detection score. So this tells us those here are good scores. And in the y-axis, we have the overlap score with the ground truth. So whoever dot which is above this line is a match with the ground truth. So, and basically what we need to do is find a point of operation. So we define a threshold where above this threshold is declared as a detection. So in that case, we will have like this region here, these points here will be true positive, these points here will be missed, and this one here will be false positive. And as you can see, there are two colors. One is green for objects that are taken in kitchen scenes, and ones that are taken in studio room scenes. So the idea here is like, how do we rescore based on the scene you see? So if we rescore, let's say, the images for a studio, so you will obtain something like this. And if we try an operation point here, you will see like we get rid of all these false positive caused by the detections on the studio room. So that's the idea, how to find a rescoring that for the detection based on what a scene you are. So we have two approaches to do that. One is based on support vector regression, and other is when we don't have explicit scene labeling, so we do LSTM. So so for the SVR part, it's quite simple. The idea is like you have a detection score, so use this as an input, and you use also the scene identity scores that you got from scene classifiers, and concatenate them. And the idea is like try to predict what will be a new detection score. So we train with this formula. So we said like it's 1 if the overlap with the ground truth is over 0.5, and other case we just keep the overlap score. That's when we know the labels of the scene. In the case we don't know it, we still know what are the different objects in the training images. So what we do is simply try to predict what will be those objects directly from each frame. And the rescore is simply a linear function. So this is the experiments we performed in the activity of daily living dataset. We sample frames every second, and we have 4 types of classifiers. And so we have two types of pairwise matrix. So in one, we assume all the penalty is equal for every change of image, and in this one, we assume like how many times we change from one type of a scene to another. That's the penalty. So these are the different results for different scene detectors. So here is when no time is added. This is a baseline, and we try with different baselines. So because we have time here, we try to apply a moving average filter, and we get some improvement. This is another improvement using a hidden Markov model. But when we try our models, we outperform all these baselines. So these are the object detection experiments. So we have 2 types of object detectors. One is DPM, the other is fast RCNN. And for the SVR algorithm, these are the details, and this is the details for LSTM. And basically, we come from this image, an image like this, that is from a bathroom, and have a lot of clutter and false detection like this fridge and stuff like that. And we're able to get rid of that because we incorporate the information about the scene. So same case here, we have this false detection of fridge here, we get removed. We have in this other case where in this living room you find this microwave, so we get rid of that. Same case here. Other case here, we have this detected as a bed, so it get removed. And other case here. So as you can see, this works pretty well. They remove a lot of false positive and in general improve object detection. So these are results for the DPN detection, object detection method. As you can see, we have SVR here, and there are 2 types. One is like when you know what's the label of the scene, and this is when we just use the output of the scene detectors. And this is the results for LSTM. There's a little improvement. It's not too much for DPM, but when we try with a fast RCNN, you see like there's a lot of difference. And in this case, the LSTM works better. So this is the end of this part, and in summary, we present experiments for scene identification. We present a formulation to improve that. and we also present a formulation to improve object detection. So this concludes pretty much the 3 topics of the talk, and so these in general are the conclusions. We show how to use the context to improve object detection in both images and videos. We have proposed a new representation to represent hierarchies in images. We also present the new problem of extracting the common context shared by several images. We have presented a new image retrieval paradigm that where the images that are retrieved are visually and conceptually related, and we also present an algorithm to improve scene identifications using temporal context. So this is a list of future work that we think that could be done after this. So for the part of image representation, so this method should be able, this tree should be able to be used in a different problem, for example, visual questioning and answering. So we think some research is needed in evaluation methods. Currently, we depend a lot in user studies. We think this representation can be extended to handle interactions with different objects, actions, and it will be really nice to have analysis of causality. So also, we think we should improve the parsing of object detection dataset using some techniques of machine learning to automatically set up thresholds and stuff like that. And for the part of finding the shared context on multiple images, so I think currently we are doing this with words, but it will be nice to have like phrases or stories instead of just simply words. And for the part of from part of the videos, it will be really nice to have a nice representation as the one that we have for images, but in this case including the scene, the objects, and the time evolution. So this concludes my talk. This is the list of publications from my years and TCF and patents, and that's it. Thank you.
Now start with